up, and they've also received and accepted 2 of the wavefront sensors, with the rest of the wavefront sensors in testing right now. Those raft towers are inserted into the cryostat grid. This is a picture of the grid. It's been manufactured. It's it's silicon carbide. It's been fired. It's been polished. All the inserts are being put in. It's coming along really, really, really well. And the raft towers then insert into those holes in that grid. And the whole focal plane has to be flat to plus or minus 11 microns, or 11 microns RMS. Really, really tight requirements on these sensors and on the whole focal plane system. And if you take 21 of these raft towers, each 144 megapixels, you end up with the 3.2 billion pixels that you're all looking forward to. I'll mention we have 2 different vendors currently providing us sensors. That is a risk mitigation. And we have some sensors from each vendor. It's possible, and I think this has been announced last year, it's possible that we will end up with a focal plane with a mixture of the 2 different sensors vendors. That's something you should be aware of. The Science Advisory Committee has looked at this a lot. On any given raft, it will all be the same sensors, but it could be a combination of rafts in some pattern, like one of those. That grid and all of the rafts go inside of the cryostat body. The cryostat body is coming along very well. The vacuum systems are provided by the cryostat subsystem. The utility trunk, all the power, all the vacuum, all the refrigeration. That large piece of the camera arrives at SLAC, well, it's built at SLAC. It arrives at INT next fall, and the raft towers start going into the camera, into the cryostat next fall. Camera body is about to have its final design review, and the integration of the actual camera body starts in January of 2018. We have a shutter, opens and closes to take pictures. That's where it fits in the camera. They are just finishing up their last prototypes to make sure the shutter works exactly as it's designed and required to do. All of our filter handling equipment is contributed by our partners at IN2P3 in France. There is a filter loader that takes filters in and out of the camera, a filter carousel that rotates which filter is going to be put into the camera, and then an auto changer that pulls one of those large filters from the carousel and loads it into the camera. Lots of prototype work there. Camera optics team has ordered a large number of very large pieces of glass. The first lens is over 5 feet across. All the big pieces of glass are in place and at the different vendors that will polish them and shape them and all of those things. Some of you may have heard that we have confirmed that glass is in fact fragile. But we mitigated that very quickly. The management team at Livermore is just fantastic. They've done a lot of optics work. Lots of other pieces that have to go together to make a camera work. They're systems engineering. They're the team that makes sure that when I get the pieces, they fit together. That's really a fantastic thing. Auxiliary electronics make sure we have power. The camera control system, it controls the camera. But it also, in order to make sure that it worked, we've been using it for all of our test systems as well. So that software is not the last thing that you do, but rather the first thing that you do. Data acquisition has to collect 3.2 billion pixels of camera data within 2 seconds, and then make it available to everyone very, very quickly. And maybe I'll just mention management. It's a thankless job. Maybe say thanks. All right, now prepare yourselves emotionally. In the next 60 seconds, I'm going to show you how to put the whole camera together. We start off with the back flange, and on top of the back flange, we install the carousel work, and currently all of that is going to be done in France, and they will deliver this already integrated and tested for me, which is just fantastic. And then we mount the camera body, and then we rotate it, and then we install the auto changer and make sure that all works, make sure it's all in the right place, and then we put in some installation rails for the auto changer, and then we put in the filter loader and make sure everything works. And then we take everything out. And then we put in the shutter and we test that. And then we put back in the auto changer. And then we mount the camera brackets and we take it out of the whole thing away, and it sits there, and now the cryostat has been fully filled with raft towers. And we attach the utility trunk, which is all the power and vacuum and cooling, we attach that to the back of the cryostat, and we take it out and we put it inside the camera body, and then the camera body goes back on the stand, and then we put on L1, L2, it's a big structure, and we align that, and we make sure everything works, and we reassemble it, and we put back in the shutter and put back in the auto changer, and then we close it all up with the sides, with the rest of the camera body, with the shrouds. Now we turn it downward facing, which is the natural position for this camera, and we do some calibration tests with something called the CCOB. It's a well-calibrated beam of light that travels through the entire optical system and confirms for us that everything meets requirements. We go back to horizontal, and it's done. And we can go home now. Except for, we're not done. So, here is the summary of my slides. The camera will be ready to ship on Valentine's Day 2020. That's the story we're sticking to. We've held that date for a very long time, in spite of all the challenges that you might expect happen on a project like this. Final hardware is being built now. We have sensors. We'll soon have raft towers. We'll soon have a cryostat. Raft towers arrive in the spring. Cryostat arrives next fall, and then the camera body in the winter. Oh, and I forgot to mention one thing. As I showed you all of those slides in the bottom right corner where the people that you're supposed to ask questions to, not me. But we have time for a question or two. So questions?
63 slides in 10 minutes.
I can do it. I may have spoken a little quickly.
Where does ComCam fit into this?
Where does ComCam fit into this? So ComCam is part of the INT. So there are deliverables for ComCam from both the camera project, that's me, and INT has that in their WBS, and from the telescope team. In mid-2019, the two subsystems bring their stuff together at SLAC. We put it together, it goes to Chile from there. Late 2019 goes on to the telescope. We take data for several months with ComCam. For those of you that don't know ComCam, that is a single raft in a cryostat attached to the telescope as if it was the full camera in a mass simulator and all of that. And then we take data until the camera arrives, or shortly there before.
Sorry, so is the raft for ComCam going to be one of the rafts in the final camera?
No, there are the two rafts that come first are the engineering test units. They're perfect in every way except for the ways they're not. They're the first ones we build, and so we're planning on using the ETU number 2 as the raft for ComCam.
Great, let's thank Kevin again.
Sorry, I went a little fast.
That was great. Thank you, Kevin. Do you want to use the body mic or the podium mic?
So Beth, I'm going to take Kevin's time, just so you know. Okay, so when we hear about the LSST, and particularly you've heard in the last couple of talks, we often talk about the incredible progress that has been made with the site, with the emergence of the superstructure above the ground, about the delivery of the M1, M3 blank now sitting in an aircraft hangar in Tucson, and as we just heard about the delivery of the first articles for the sensors. What I thought I would do is I'd take a completely different perspective on the LSST. And I was trying to think of an analogy to give you. And if you remember when you were a kid, and you're having your breakfast and you're pouring your cornflakes into the bowl, and you take your grubby little fingers and you're reaching inside to try and get that free gift inside the cereal box, you can think about the LSST as a box of computers with a free gift inside. I don't know what that background noise is. Where the camera and the telescope come for free. Now, when your telescope costs about $500 million and the camera is about $180 million, free is clearly a bit of a relative term. But the reason I was trying to come up with this analogy is because if you think about the computational resources that we have available at the end of the survey, we'll have about 1.8 petaflops of compute power to process the 10 years of the LSST survey data. About 200 or 150 to 200,000 cores, all working on tens to hundreds of petabytes of data. And if you actually built that system today, it would rank within the top 50 supercomputers available in terms of its raw computational power. And so this means that when we move to an era of large data sets like the LSST, the software and in particular the algorithms are as important to the science and the processing of the data as the cameras and the telescopes are actually building. And so what I really wanted to talk about here is to just give you a brief introduction to some of the algorithms that are changing the way we're thinking about data with the LSST and with the data management systems. And in particular, one of the core aspects of LSST science is the generation of alerts, the generation of detecting these transient moving variable sources. And this has been made possible by the development of algorithms led by our own Robert Lupton, with Allard and Lupton, that allow us to take separate images observed on different days with different image quality, to match the image quality from one image to the next, and allow us to subtract one image from the other, to identify anything that has moved or changed or varied between those images. Now, one of the real challenges is that not everything that you detect is a real astronomical event. Not everything that you see, not all that glitters is not gold. And so this shows you the subtraction of images where the processing didn't actually work particularly well, where you get false positives in terms of the detected events. And if we look at current or existing telescopes like the Palomar Transit Factory or the Dark Energy Survey, then the number of false positives that we're detecting or are being detected in those surveys can be between 10 to 50 times the number of transient events that they're finding. And if you remember that we're going to detect about 10 million variable sources in the LSST every night, then these sorts of ratios are really challenging for us and challenging to the science. And so what I think one of the biggest impacts on survey astronomy over the last decade, particularly when we start thinking about the transients and the variable sources, is the development and the application of machine learning techniques to our data streams. An example of this is the series of decision trees, or in this case, random forests, that are used to classify not whether an object is a particular astrophysical type, but whether it's real or whether it's fake, whether it's real or bogus. This technique, this random forest technique, which is just a sequence of decision trees, all brought together, each one of these machine learning algorithms voting on whether this object is real or not. The Chicago approach to voting, where you vote early and you vote often. And by taking these votes together, we actually can end up with classifications where instead of having 10 to 50 to 1 in terms of the number of false positives, we get down, the PTF was getting down to 2 to 1. And this enables you to make discoveries like supernova 2011 FE, one of the earliest detections in the rise of that supernovae, or the discovery of whole new classes of supernovae, the ultraluminous and the hyperluminous supernovae. So one of the techniques that you'll hear from data management tomorrow that Colin Slater will be talking about is by putting the smarts and the intelligence not just into the machine learning algorithms, but into understanding the properties of the pixels and how we actually process the images. We can actually modify and build upon the Allard and Lupton algorithms, taking into account the correlated noise within those images, and actually begin to determine reduce the number of false positives themselves down to what was comparable to what the PTF was finding after applying their machine learning techniques. And so by understanding the noise and the properties of our images, we can get close to these machine learning techniques. And this enables us to now apply machine learning onto the classification itself. Yeah.
Are you taking questions?
I'll take them at the end if that's okay. But it's not just applying machine learning or algorithms to weed out the junk within the data. It's always how you preserve the information. So this shows you an example from the data management group put together by Yusra Al-Sayed, where on the left-hand side you see an image taken from the Sloan, where you can now see how we subtracted out the background. And you can see how that background subtraction subtracts out the halos around the bright stars, but it also begins to over-subtract around the large galaxies. And so this biases the photometry if you're measuring photometry of sources behind or next to these big galaxies or bright stars, as was found by Rachel Mandelbaum and her team when they were looking at lensing of background galaxies by foreground galaxies. It biased the actual photometry. But by developing algorithms that take an image, this is an SDSS image, and now co-adding those images. So co-adding in the images where you model not the background, but the difference between difference in the background from image to image. You're modeling the non-astrophysical background. You're modeling the scattered light, and you're subtracting off the scattered light. And then co-adding these images with 55 epochs, compared to the 140 epochs or so, 160 epochs we'll get in each individual passband for the LSST. You can now actually preserve, as you can see here, the large-scale structure in terms of the diffuse emission from the gas within our Milky Way. And so by being smart about the algorithms that we apply, we're actually preserving information and preserving the science that we can extract from these images. And this is what will enable us to do the processing of these petabytes of data, of detecting the tens million alerts or variable or transient sources each night, of detecting the 20 billion stars and galaxies within the 10-year data, and also to actually serve these data to the community. And one of the things we often talk about when we talk about this era of the LSST is big data. Right? So this is big data. We're bringing in petabytes of data. But I think this is the wrong way of thinking about the LSST and thinking about the LSST data itself. Because it's not about data, it's about information. It's preserving information and using algorithms that will allow us to preserve that information. And so, I mean, if you look at where the commercial community is today, then if you look at Instagram, in Instagram, there are 1.7 million likes on the images stored within Instagram every minute of the day. That means 1.7 million interactions with data every minute of the day. With YouTube, they upload about 300 hours of video every minute of the day. Right? If you take that for a whole year, that's about 400 petabytes of data if that video is in high definition. So even today, the community, the commercial community, is working with data volumes that exceed what we will achieve within the next 10 years and are comparable to surveys such as SKA will be generating when they come online. But the important thing about it is it's not the hundreds of petabytes of data. What matters is, if we think about the YouTube videos, how many of those 400 petabytes of data do you actually interested in terms of searching through the data, right? So it's all about information, right? If you are interested in cats licking lollipops and you come across images from the SDSS, that's not a successful search, right? So your search and the information that you're doing relative to what the scientist next to you is doing is very different. And this is what we have to be able to achieve. So we're moving to an era where, in fact, we're moving back to the real era that we used to be when we did analysis. We took our data, we built our models, we used inference to build the models. We're now changing to a place where we take the data, we process the data, we generate catalogs, we do inference to generate our models about the universe. And the data processing is as integral to the inference that we can do for those models as the data themselves. And we're also moving to a regime where the project and the science is actually integrated in the sense that the project is doing the data processing, generating the catalogs, and the algorithms that are being used in this whole process generated by the project impacts the type of science that we can get out. And so what I wanted to do is to just end with an example of how, by thinking about the data in different ways, we can extract more information than we would expect just by naively thinking about 2D images on the sky. An example of this is how we can change our expectations that we wrote down when we wrote the science books for the LSST, and how by thinking about the data again in different ways, we can actually exceed many of these science cases. So this shows you an example, an image from the Pan-STARRS survey, a 1.4 gigapixel camera. I believe it's the largest camera in operation at the moment. Greg Green and collaborators took 800 million stars measured in the Milky Way from Pan-STARRS and created color magnitude diagrams from it. And from these color magnitude diagrams, they could estimate the type of the star, and they could also estimate the distance to that star. And from the distance and the type, they could also estimate the dust or the reddening. And not just the dust or reddening in terms of some global map like you get from Schlegel, Finkbeiner, and Davis, but the reddening on each individual point on the sky. And so from 800 million stars, they could actually recover the three-dimensional distribution of dust within the Milky Way, uncovering rings of dust around Orion in the radial direction that we couldn't actually come just by thinking about having a two-dimensional image on the sky. And so if we have 800 million sources were used to actually detect or measure this three-dimensional distribution of dust within our galaxy, think about how much we can actually do when we have 20 billion stars within the Milky Way. And so I think what we're finding now is that the algorithms are as important to us as the camera and the telescope, and actually putting emphasis and development into those algorithms now, and the processing of the data enables us to really realize the work and effort that went into the construction of the camera and the telescope itself, and the optimization of this survey. And so I think it's an interesting time for us. And I think what we need to be thinking about, and what the data management group is actually thinking about, is how we actually take these new algorithms and how we use that to preserve the information. And we're actually investing resources. We talk about large data, but it's not actually the computational resources that we're invested in, but the actual people who will actually develop and build these algorithms. Thank you. So we've actually done a number of trade studies associated with the, if you have a mixed focal plane. We've looked at the implication for the sensitivity or the depth as a function of position on the sky. And within 10 years, I mean, after about 2 years, there's no real signature left in terms of the actual depth. I think the biggest potential impact on the survey is generating templates to subtract from each image that's coming out. So if you had to generate a template, for a specific type of sensor, then it takes, instead of taking 1 year to cover the sky, it takes about 2 years to cover the sky. And this is only really important in the G band. And so it pushes out the length of time that it takes us to generate these image subtraction templates. But I think the important thing to remember is, as we observe, we're observing at a range of air masses. And so the effective throughput that we're seeing is varying much more than the effective throughput you would get just from moving from one sensor to the next. And so the astrophysical variations across the sky are significant relative to the sensor variations. Yeah, David.
So actually, it's a quick question on what you just said, which is, why is it more important with the G-band than the other filters?
It's just the number of observations that you have in each filter and how rapidly you come, as you rotate and you come back to cover the field.
So my real question is, in the random forest, do you have a sense of the rate of false negatives, that is, real things that get shuffled off with the false positive lane?
Right, so with all of these algorithms, the threshold is a trade-off between the rejection of real data and the rejection, and so it's trading true positives versus false positives. So that threshold determines how you're throwing away the baby with the bathwater, I guess is the idea. It's not clear, I think, at the moment, because the training sets that we actually use are devised to answer specific science questions. And in fact, LSST is in a slightly different place, so we're trying to be very broad with the science. So I'm not sure how we would actually characterize the number of true positives that we're actually throwing away.
Okay, can we hear me? Right, so, no. Is there a button? Really? You can't hear me? I'm so loud. That doesn't usually happen to me. Is it good? Okay. All right, I'm gonna hold it. All right, so hi, another change of tack. My name is Frossie. I'm working with the Science, Quality, and Reliability Engineering team of data management for LSST. This is a completely different talk. All the work described here was done by these fine people you can see there. The opinions, especially the wrong ones, are all mine. And I just want to clarify that Ben has kindly allowed me to eat into his time, so we're not behind schedule, we have replanned, just to be clear. So the subtext here is how I learned to stop worrying and love Silicon Valley. And I think you're going to hear some of the same themes that Andy has just talked about. So I want to talk a little bit about the cloud computing architectures that we are now using for LSST and in other projects. And I just want to say that the main advantage that we are using these things for is that in many of the modern cloud compute architectures, developers can self-service. They can actually fulfill many of their needs that were traditionally filled by external IT service providers themselves. And when developers can self-service, this brings them happiness, and it brings their manager profit, because happy developers are efficient developers, and they cut down a lot on the time that they're held up waiting for things to happen. So this is the digression part of the talk. When I first got into this field in my first job, I remember being incredibly excited. We had these Sun pizza boxes, as we used to call them, and if you spend an absolutely obscene amount of money, you could actually put 256 megabytes of RAM in them. And now there are 2 gigabytes of RAM in my phone. You can keep your flying car. I don't care. This future that we got is actually even better as far as I'm concerned. However, what happens with dinosaurs like me is that we grew up in a scarcity mindset with compute resources. When you go look at my photo feed, this is not like an Apple ad. You don't see beautiful landscapes or Instagram filters. What you see is me taking pictures to aid my failing memory of things like the Wi-Fi code for a conference. So I see myself doing this. I am now taking a 1.9 megabyte image to capture 8 digits. So at least part of me has gotten the message that space is not as much of a constraint as it used to be. However, somehow when I go to work, I sometimes forget this. We have actually now, in the trade-off between human time and compute resources, be this compute or storage, actually human time is often far the most expensive of the two. And this is actually something that's very easy to remember in a project like LSST, where we track very closely our expenditure on staff time. It was a lot harder to remember when I was in a more academic type environment. I don't really read Twitter, but people send me things which usually infuriate me, thus confirming why I shouldn't read Twitter. So somebody said that it's a good idea to write obituaries for your machines that die. Computers are not pets, okay? Don't do that. Don't think of machines as precious resources. It actually leads to really bad architectures where you're very dependent on special snowflake setups on your particular machines, and then the machines die, and then you're in big trouble. We are now in an environment where we really should think of computing as what happens when you turn on the faucet and you get water out the tap. You don't like write obituaries for each droplet of water that comes out of your tap. Carrying on to the advantages of this kind of cloud-based wonderful world that we live in, we have huge developments in reliability. We always, those of us who have been involved in IT, we always cared about uptime, okay? We weren't cowboys in the past, we still cared about these things. But perhaps we actually cared about it too much. I remember, being in the Barr at the computer conference, and everybody was like, my file server has been up for like 14 months, and another one would say, well, my file server has been up for 18 months. And now if you say that, people will look at you in horror and go, when was the last time you did any security patches, right? So it's no longer about uptime, it's really about reliability. And our users and our community's standard of what is a reliable service has really shifted. They have been trained by Google, by Facebook, by Twitter to be available. This is the GitHub API server reliability. When I took that screenshot, when people are used to that level of reliability, it's very hard for them to go to work and find that the network is down or the server is down for maintenance or all these things. We need to kind of match their expectations. I actually took a picture in LAX. Don't have a heart attack in LAX. It's clearly a bad idea. There are real architectural advantages in software. I'm going to have to speed through this bit because I don't know that anybody is interested. But a lot of these architectures are very modular in nature. It allows us to double dip and triple dip in using a system in multiple contexts. This is the diagram of Jonathan's, who's here, architecture for the documentation system. And it takes advantage of many kind of off-the-shelf components and architectures that we are then reusing for other projects, and we're getting much more leverage from that work. That kind of design actually allows us to also keep the architecture fresh by taking out an agent component and replacing it. And what is great about these things is that you find a component, and in many cases, commercial off-the-shelf components that do a fantastic job, and then your job is really to link them together in a way that is actually, maps your workflow. These are some of the services that we're using. I keep thinking we're going to move to Slack, so I keep putting in the slides. It'll happen eventually. Some of these are actually cloud-hosted. Some of these are cloud-hosted free, some of them cloud-hosted paid. And for example, our Jira server is actually internal because cloud hosting our Jira server didn't actually make sense. So we host that ourselves. So it's not about being dogmatic about it, it's about doing the right thing that works. And another advantage of this, which of course is a great concern to us, is a lot easier to scale in this kind of architectures. And this is something that we're very mindful of as we're producing systems right now for developers, but eventually we might wish to scale them to the community at large. So what worries people when you go out and preach this model? And it's always the cost. People say, we can't afford the cloud model. I have seen people spend months trying to find somebody to lend them computers to reduce their data, when they could have reduced their data in 3 weeks on a commercial provider with much less expenditure of their time. And people really eventually, after the talk, somebody will go and write their numbers down and go to the Amazon Web Services page and cost them and come back and say, but Frossie, it's ridiculous. Look, it's thousands of dollars. The problem is it's not, okay? So again, we have this mindset when people go and cost their ability to do this, they often actually try to calculate, okay, how much data do I have to upload, and then what do I have to do to process it, and then to download it again. One of the things that we actually realized is that the majority of the cost is actually dominated by data out. It's actually outgoing bandwidth that most of these places charge for. And so the trick is not to actually get your data out. When you have services that are all co-located and consume the data between themselves, your costs actually drive down dramatically. And so that is how it's actually possible. And it's also not just about compute. It's not just about data processing. These are some of my monthly bills. Route 53, which is a DNS service, $1.54 per month. This is going to be the best $1.54 that I have ever spent in my entire career. This allows our developers to very quickly get their own address space for a machine rather than have to go through asking somebody to give them something. So they can spin up domains for their document, for their service, for their prototype very, very quickly. It's totally, trivial in the scheme of things. It's not even like a Starbucks cup of coffee. Our data transfer, this is actually to prove that, we're running our quality analysis harness in this environment, but the quality analysis harness is consuming the same data over and over again, and we're only interested in a very kind of compressed view of the output, which is essentially our key performance metrics, and so we never actually pull the majority of the data out. And so our data transfer costs are very, very low, and our file storage costs similarly, because again, you're dominated in this kind of billing model by data transfer. It's also worth knowing that IT is never free as in beer, even though you should be buying your sysadmin's beer. It's especially for universities and other academic groups that do not have major computing facilities, they don't have their own machine rooms. It's actually very difficult to obtain these things, and you are somehow paying for them, even if it's indirectly. And in particular, I never got charged for electricity whenever I was managing an IT group, but in fact, electricity is actually a major part of the cost of operating an ongoing data center. And it's worth pointing that this is an argument towards a certain type of architecture. Private clouds are actually clouds too, and they're increasingly available both from universities having their own OpenStack cloud systems. Of course, it's available to us at LSST through the NCSA Nebula OpenStack cluster. We have many of the similar architecture advantages. In some cases, you may not even be paying for them because it's a facility that is provided through your university. Now, these things are actually very non-trivial to set up and operate without the kind of specialized know-how that you need to operate the system. But if you can actually find one, or if you can buy a turnkey system, it's fantastic. And there are clear, obvious moves for funding agencies across the sciences to develop things that might lead eventually to an NSF cloud or some kind of service like that. So it's worth being ready for them when they come. And certainly on the scale of LSST data usage, things like that will be available when our data is actually out. Purchasing rules and grant rules, I will admit, depending on your grant system or your university system, it does actually make it very difficult in some cases to build those things. A lot of the grant rules are oriented towards buying your own computers. I'm hoping this is something that is actually going to be changing. And the real, architectural objection to this usually is, but what about vendor lock-in? Why, using a commercial service or a specific, cloud architecture is dangerous because it will kind of lock you into it, and then if you ever want to go back to your own hardware, you won't be able to. And this is actually just not the case in my experience. I actually did a Google search for messy computer rack on the internet, and I'm convinced this was actually my Hawaiian IT room. So if it isn't, I can't tell the difference. I used to operate a team of sysadmins that would maintain a machine room like that for my Mauna Kea Observatory telescopes, and now this is literally the only piece of hardware I own. I think this is an actually improvement, especially since I don't have to feel guilty about the state of the cabling. And this is one of those things where once you have actually gotten into this model where you have a very kind of thin set of computer resources at your end, but you have a pool of resources in a cloud environment, it's very difficult to kind of go back to the old model. And the quote is, after a long weekend with your phone, you learn what's really important in life, your phone. This is kind of how I feel about my laptop, actually. And the final kind of philosophical point, this is where I get the Frossie, you have sold out to Silicon Valley talk. We grew up in an environment where corporations were evil. The kind of people developing the systems that we all use, the GitHub people, the Dropbox people, the Google people, they are the people like us. We won. They're all open source people. Guido Barroso works for Dropbox, for you Python groupies. They are putting massive amount of work back into the open source environment, and so I don't have any concerns about that. going to speed up a little bit. I just want to say that we are using a variety of these architectures wherever it makes sense, wherever it's easiest for us to get going. Some of it are commodity cloud providers. Some of it is our private clouds like OpenStack, in our particular case at NCSA. We use software as a service providers. GitHub is infinite value for money because it costs me nothing. In some cases, it might make sense to have your own metal. For example, if you want a macOS build slave, it's actually not possible to get virtualized macOS slaves for that. And so that's the case where your own hardware might actually make sense. Square actually hosts right now a number of production-level services with fabulous availability to support the DM development process, including our computer integration systems and our science QA harness, which is developed in-house, as well as many of the communication tools and platforms that you're using, such as our Discourse forum, which is a community.lsst.org, and of course the infrastructure that we use to make the LSST data releases. And these are some of these technologies that are underlying these services, the AWS platforms and the OpenStack platforms, both of which are architecturally very similar, so even though they're not identical, moving a service from one to the other has been relatively painless. We're now, everybody's looking at Docker orchestration. There are teams in LSST DM looking at Kubernetes and Swarm and Mesos, and that's clearly the next step along this chain. And we are very much interested in rapid and movable deployment, partly because we're developing tools and services that we might think our community might eventually want to run on their own private research facilities if they have their own LSST data as part of the Level 3 program. And my final quote, which actually I realized that Andy's talk was actually very similar, this is kind of an important thing. If we are technical leaders here, and it's very important to worry about the people more than we worry about the tech. And there's always a ease of doing the same thing you've always done. It seems easier and safer, but LSST is a project with a lot of really young developers, and it's important to us when we're judging the trade-off between adopting a current technology or doing it the same old way to think about what prepares our young contributors for their career in astronomical software. And I think it's very important to skate to where the puck is going to be, and that's another reason that we are embracing these technologies and exposing them to the data management team. Thank you very much. I'm done. Questions of views? Fantastic. Ben, all yours.
You waited for about a millisecond.
Yeah, I know, right? I think I am going to bolt, but you can find me outside.
Can everybody hear me okay? Good. So, since I'm a relatively new face among you, I wanted to start off with introductions. My name is Ben Emmons. I'm the new LSST EPO project manager. I came onto the team this past April. Before that, Suzanne Jacoby was taking on the Herculean task of managing both communications and EPO, not to mention large conferences like this. So she's very happy. She's smiling a lot more nowadays that I could come in and help offload some of that. In addition, Tim Axelrod has been an EPO scientist with our group for some time. He recently announced his retirement. I think the new Cessna that he purchased has something to do with it, but that's just a suspicion. Emily Costa, she's an incredibly gifted webmaster. She does all the graphics design. She does, for example, the incredible design on the t-shirts that all of you have received during the conference. She just is everywhere, so we're really excited to have her help also in the video component with doing multimedia. And then finally, Suzanne has collected a great outreach advisory board to help kind of support and lead and provide us kind of a springboard for ideas. That kind of group was put on hold, temporarily disbanded, because we're in the process of doing a little bit of a reorg. As I mentioned, I came in April, but also we're in the process of looking for a head of education and public outreach. As you know, the major subsystems within LSST are co-led, and so this would be an individual coming in to help me lead the EPO effort moving forward. And so the Outreach Advisory Board will kind of come in after that, and we'll reorganize. In addition, Ed Prather is a consultant. He helps out providing some education background. He's an astronomer at the U of A. And then Ellen Bechtel, this is kind of hot off the presses. We're excited to have her as well. She's coming in as an evaluation specialist. She has a background in informal science. She's worked with, for example, the Madison Science Museum. She comes from Madison, Wisconsin. She also participated in the IceCube neutrino project. So just an incredible person with diverse skills, and we're really excited to have her on. And then more to come. You saw the mention about Tim Axelrod, so we're going to be looking for that scientific component for EPO. And then there's also going to be some development kicking off, and you'll see some of that in my slides coming up. Okay, I am very aware that I am the only thing between you and lunch. So I'm going to move quickly through slides to get you where you really want to be. But if you are a one-pager kind of person, if you want a takeaway to say, okay, what is EPO? Communications has done a great job putting together a fact sheet that just lists on one page what EPO is all about. So this is a really neat resource to have available if you're in conversations and you're like, hey, you went to that LSST thing. What's the EPO group up to? Now, this is something you can hand to them in an elevator and look like a genius. So bookmark that URL. All right, so we have a lot of questions that we get from various parts within the project, and I wanted to highlight some of the common ones. What's the connection between EPO and data management? For those who are aware, there's a very strong tie between those two subsystems. What data will the public get compared to the data available to the professional astronomers and those within the LSST consortium? So I'll cover that. Where will it be served from, and what will the interfaces potentially look like? Let's start off with DM. We love DM. DM is really the subsystem we work most closely with. They are our gateway into the LSST data. One of those areas is the alert stream. This is a key deliverable that LSST Telescope is going to be providing to us. Now, 10 to 20 million alerts a night, that's kind of like a fire hose. It's just way too much for the general public. So EPO is going to kind of siphon off 10% of that. Still, at 1 to 2 million alerts a night, that's still too much to consume for most people. So EPO is going to be adding value by providing filtering on that pipeline of alerts, allowing people to kind of drill down into just the alerts that they care about. Hey, I just care about supernovae, or I just care about asteroids, or I just care about this slice of the sky. So that's kind of part of what we work with DM to get, and how we're adding value to it as an EPO program. Image collection, image delivery, image cutout, so there's going to be an optical component as well. One of the neat things from a public perspective is this concept that LSST is going to be almost like a movie of the universe. This word movie comes up a lot. And even though it may not have a whole ton of astronomical value to see kind of a time-lapse movie, it's really cool for the public. They like seeing this like visual change. And so there's going to be that component, as well as some of the classroom research using the optical data. The annual catalog subset. So once again, similar to LerStream, LSST is going to provide a massive amount of data, just far too much data than anyone in the general public might need. And so we've decided to take a subset of that and call that the public subset. And we're looking at about 700 terabytes annually. And that's kind of, again, 13% of the full LSST catalog, and you're thinking, wow, 13% doesn't sound like 700 terabytes is a lot of data. There's a lot of really cool stuff you can do, whether that be classroom, whether that be citizen science, whether that be amateur astronomers, whether that be informal science and planetariums. That's just a lot of data to work with. So it's still a good thing. In addition to all the data we're getting out of DM, we're learning a whole lot from them. They are really paving the way for us. EPO starts a little bit later in the LSST project schedule by design, and so we're coming in able to see some of what they did and learn from what they did so we can kind of leverage their best practices. All right. We're not just stealing DM's cool stuff and slapping an EPO label on it. We're doing more than that. We are excited about, this web portal I mentioned showing off this transient concept of how the universe is dynamically changing over time, and then also giving access to the data set. I really liked what Andy said. It's not all about big data, right? There's more to LSST than big data, but the data is a big part of it. So we want to make that as easy as possible for the public to consume and to leverage and use and research and discover. Public alert stream. So there's this concept that Suzanne Jacoby pioneered with her group. They put together a mobile app. Imagine you're an astronomer, like a hobbyist in Australia, and you've got a nice 10-inch telescope in your backyard. You want to know where to point it to that night. It could be a little bit of guesswork. It could be looking at, star catalogs and whatnot. But wouldn't it be neat if you had an app that told you right now something amazing is happening if you point your telescope right there? And so this mobile app was developed as a prototype. It used the Catalina Sky Survey as its back-end data, and it was really popular. So we're hoping to kind of build on that and kind of refine it and make it a little bit more accessible. Zooniverse, for those who are in the citizen science world, they have really put a lot of work into creating a framework for citizen science, and they have this massive community that we're hoping to leverage. Just as a little plug, in September 12th and 13th, EPO is hosting an unconference on the citizen science topic. So if you go to community.lsst.org and search for citizen science, you'll see some details. We're bringing in Chris Lintott to kind of be a special guest for that effort. We want to get into the classrooms. That's not easy, right? Just because we have the data doesn't mean teachers are going to be clamoring over themselves in order to incorporate it. This stuff can be scary, let's be honest. Like, teachers are busy. They have a curriculum they've already worked with that they know and they trust. We need to provide them the necessary tools and the training to understand how to leverage LSST data in the classroom. And we have to be creative too. It's not just about astronomy or physics. There's math with statistics. I was even talking to the Space Telescope, and they mentioned that they interact with classrooms using reading comprehension, reading an article about Hubble. So anyways, opportunities within the classroom, and finally planetariums. This is where a large amount of the public is going to be moving through. I'm not going to dwell too much on this because Frossie already sung the praises of the cloud, but we are going to be leveraging the cloud a great deal. We're going to be taking that data that we're siphoning out from the full data set and storing it in what we're calling an EPO center, and it's going to be cloud-based. And then just real quick, I wanted to kind of put out in front of you some concepts that we're just playing around with. These are just storyboards, these are ideas, these are just kind of concepts, so don't tweet this out to the world and say, this is what LSST EPO is going to be doing. This is just, some ideas. These are actual screenshots from that mobile app prototype, kind of described it. Citizen science projects. There are a lot of citizen science projects that already exist today that are doing a lot of what we want to do. And so, fortunately, we're going to be able to leverage that. And one of them that I'm kind of in love with is this asteroid zoo. Fantastic interface. It has a tutorial, a wizard. It was incredibly successful. It was one of the if you go to it, you'll find that they've closed it down. They've shut it down because the data has already been moved through. There was so much public interest in helping out that they were on a record pace for moving through that data and getting it all cataloged. So, it just shows that there's interest out there, and if you add a little bit of polish and you help people through it, people want to be a part of it. Classroom activities, this is an actual example from Dan Reichert's Skynet group. They partnered with the University of North Carolina. And the idea is here are all these automated telescopes that are positioned strategically throughout the world. Students come in and they can remotely take image data from these telescopes and then use that image data inside of an educational curriculum. And so there's this process of bringing that data into the classroom, observing it, working with it. This isn't some pre-canned little thing like, oh, you know, this has already been done and we're going to walk you, handhold you through it. This is real stuff. They're really looking at it. This is real data. And they're having to kind of think through challenging questions just like an astronomer would. This is an undergrad base, but there are other great programs out there that also work within the K through 12 world. Multimedia is a big one. A lot of times I feel a little bit jealous of Hubble and James Webb, right? Because they've got those high-def, ultra incredible pictures of nebulae and whatnot. And I feel a little bit jealous because a lot of the data coming out of LSST is wide field, and so it's just lots of like, you know, blurry dots of light. But there is still amazingness to be had with LSST, especially in our understanding of dark matter, dark energy, galactic structure. And so these are just some simulations and some visualizations from Ralph Keller out of SLAC. There's a lot of opportunity here to take that data coming out of LSST and visualizing it for the public. And Andy also touched on that with the dust clouds. So really exciting work. And finally, even though it's not all big data, a lot of it is big data. You need big data tools to work with that level of data, with that scale. And Andy also referred to the fact that this has been figured out, where we're not paving the way in this realm. And so this is an example of a product named Hue. It's an open source project from a company called Cloudera. They're a major name in big data. They have kind of this widget type modular architecture, so allows you to pick and choose what you want to display on your screen. They leverage some other open source projects like Solar, which is open source search engines. So if you go onto like Amazon, you're searching for clothes, and then you're like, okay, well, clothes for men. Okay, I want pants, and you see that like all of the listed items are updated and kind of narrowing the results. That's kind of what search engines provide with faceted search capabilities. And then alert streams, right? That's a lot of data that we are streaming out. We need a workhorse to be able to handle that much data and streaming it out to the public. And so projects like Apache Spark, Apache Kafka, these are the kinds of big data tools we're going to need to leverage in order to take advantage of that. So with that, if you're interested in getting involved, if you like EPO, if you know people that want to get involved with EPO, we have that community resource available to you. We're on Twitter. If you have access to the contacts database, my information's in there as well. Feel free to reach out to me, phone or email. I'd be happy to talk. So thank you. Any questions? I know that, oh wow, that's great.
So we'll take one question, and then I invite you to eat lunch with Ben, since we're just running into the lunch hour. And I'm not sure if Chris or John raised his hand first. I'll call on John, and then because Chris can grab Ben as he walks away.
This John?
Yes.
Do you have a number of universe-related projects sort of ready in the pipe? I mean, there's the obvious, you know, just redo Galaxy Z1, but and an asteroid rifle. But do you have a number of those already sort of developing?
Yes, so the question is, do we have citizen science projects specifically with the Zooniverse framework ready to go? If you go to that community post that I mentioned, it lists all the citizen science projects on Zooniverse that overlap with our objectives. So that's kind of like a guiding light as far as projects go. Part of the challenge with citizen science is you kind of need data, right? There's only so much you can kind of prepare with the UI, but ultimately it comes down to the data. Without some of that data, we are looking at, without the LSST data, we're looking at other data sets from other scientific and astronomical projects that we can kind of use to prototype it out. And so, yes, we are kind of in the works for preparing some ideas for that. Good question.
Great, so let's thank Ben and all of our speakers and go ahead.